Hello friends, welcome again. Today we'll be doing a problem related to fault, and here we are given a turbo generator which is 100 MVA and 11 kV, 50 Hertz, and a symmetrical fault is done at its terminals, and the short circuit capacity is 500 MVA. Okay, the neutral of the alternator is grounded through 0.05 per unit, and the zero sequence reactance of the generator is 25% of that of the positive sequence reactance. Okay, so he's asking us what is the short circuit capacity for line to ground fault in MVA. So let us see how to proceed. Okay, so he has given us the short circuit capacity in MVA. So let us calculate that in per unit first. So short circuit capacity in per unit is equal to whatever is the MVA given divided by the MVA of the generator. Okay, the MVA of the generator is 100 MVA, and the short circuit capacity is 500 MVA, so it is 5 per unit. Okay, so if you take the inverse of this, you get the impedance in uh, the positive sequence impedance in per unit. Okay, why you get that? Because say this is my generator. Okay, so this is the voltage and this is the positive sequence of the generator, and a fault is done at its terminal, so this will be 1 per unit. Okay, so my 1 over x1 is going to give me uh, 5 per unit. Okay, so this 5 per unit is the current, or this is the power also. Okay, same. So if I calculate x1 from here, I get it as 1 by 5, and this is also this will give me 0.2 per unit. Okay, so now the positive sequence impedance is known to us, that is x1 is 0.2 per unit. Now let us say that our x2, that is the negative sequence, is nearly equal to x1. Okay, because no data is given about it, so that is equal to 0.2 per unit. Okay, now we are left only with x0, which is a zero sequence, and here he says that the zero sequence is 25% of the positive sequence, so it is 0.25 of 0.2. Okay, so if you calculate this, this will come out to be 0.05, okay, per unit. So now x naught is also known to us, and when x naught is known to us, then what we can do is, now we can calculate our short circuit capacity when a line to ground fault occurs. Okay, so let us proceed for that. Now you know that when line to ground fault occurs, then the sequence impedances can be written as, this is x1, this is x2, this is x0, all will be in series because all the sequence currents are same. Okay, and here this is thrice xn. Xn is the impedance by which you have uh, grounded the alternator. Okay, so here this is a scenario. Now this is 1 per unit. Okay, the voltage is 1 per unit. X1 and x2, we know that we have already calculated x1, and that is we have considered equal to x2, and it is 0.2 per unit. This is what we know. X0 we calculated it, and it is 0.05. Okay, and xn is also known to us. Xn is given as 0.05 per unit. Now you know that the current, this I1, positive sequence, negative sequence, and zero sequence will be equal. So I1 equals to I2 equals to I0. Okay, and this will be given by if we apply KVL here and solve this equation, we get 1 over whatever are the impedances which are coming into this loop. So it is x1 plus x2 plus x0 plus 3xl. Okay, so if you calculate this, this comes out to be 5 by 3. Okay, now we know that the current which will be flowing will be thrice of the current which we have found here. Okay, so please remember that it will be 3 times this current. Okay, 3 times I1. Okay, so it will be 3 into 5 by 3, so it is 5 per unit. Okay, now this is 5 per unit of current, and this itself is 5 per unit of power because your voltage is 1 per unit. Okay, so you know that uh, this is in per unit. Now you need to convert it into your MVA, so you have to multiply it by your base. Okay, so the line LG fault capacity is 5 into, with that is per unit, in per unit, into 100, so it comes out to be 500 MVA. So this is the answer to this question. Okay, so this is how you need to proceed for the problems where you have been given the capacity. Okay, so thanks for watching.